Assalamualaikum warahmatullahi taala wabarakatuh. Welcome to another video on signal and system analysis. So in this video I will show you how to solve few problems related to periodic signal, energy signal, power signal, even signal and odd signal. Okay, so let's have a look at the first question. So in this question we are given a few graphs, okay, a few plot of signals, and we are asked to determine the fundamental period, okay, T, fundamental frequency F, and angular frequency omega of each of these signals. So let's have a look at the first one. Okay, signal number 1, we are given this square wave like this. So we know that fundamental period, okay, is the time taken to finish one cycle, right? So if we look at this signal, let's say I start from here, okay, and I go like this, go down and go to the right and go up. Okay, so at this point, okay, I'm going to if I go again, I'm going to repeat the same cycle or the same pattern. Okay, so I can say that from here, from t equals to 0 until t equals to 2a, I have one period, okay, which is equals to 2a. So let's assume that this time is in second. So we have t equals to 2a second. Fundamental period is given, fundamental frequency is given by 1 over t, okay, so 1 over 2a, and the unit is hertz, while omega is given as 2 pi f, or you can also use 2 pi over t. Okay, so 2 pi over 2a is pi over a. The unit is radian per second. Now let's have a look at the second signal. So in this one, if we look, let's say we start from here, from point 0, 0. Okay, if we just follow the graph, go up and then go down, and then from here, if I go up again, I'm going to repeat the same pattern. Okay, so it means from here t equals to 0 until here t equals to b, I have one period, okay, the fundamental period. So again, let's assume the time equals to second. So we have here t equals to b second, and the fundamental frequency is 1 over t, so 1 over b hertz, while radian frequency equals to 2 pi f or 2 pi over t, so we will have 2 pi over b radian per second. For the next one, this is a triangular signal. Okay, so again, let's say we start from here, from point 0, 0. Okay, if we just follow this graph, it go up and then it go down, and then from this point, okay, t equals to 2, if I go up again, I'm going to repeat the same pattern. Okay, so I will say that from here, okay, from t equals to 0 until t equals to 2 is the fundamental period, so it's 2 seconds. So t equals to 2 seconds. Fundamental frequency is 1 over t, so it's 1 over 2 hertz, and the omega or radian frequency is 2 pi f or 2 pi over t, so it will be pi radian per second. Right, now let's have a look at this signal number 4, should I call it? Right, so again, let's say we start from here, this point 0, 0. Okay, Now if I just follow the curve, go up and down again. So here from t equals to pi, if I go follow the curve again, I am now repeating the same pattern. Okay, so I can say that this is my fundamental period, okay, which is equals to pi. Now you can also start at a different point. For example, let's say I wanted to start from here, okay, t equals to 2 pi. So if I go up and down, I follow the curve, so until here. If I go up again, I'm going to repeat the same cycle or the same pattern. So I take the period, okay, from the point where I start to the point where I end, okay, and if you calculate this will be pi as well, okay. 3 pi minus 2 pi, it will give you pi. Okay, so you will get the same value of fundamental period, which is t equals to pi second, and the fundamental frequency is 1 over t, so 1 over pi hertz, and the omega is equals to 2 pi f, or you can use 2 pi t, so it will be 2 radian per second. Okay, now another signal, so number 5. So let's say I start from here now, okay. Let's say I start from pi, so I go here, okay, and then I go up and I go down. So starting from here, if I go again, I'm going to repeat the same pattern. Okay, so I take the point where I start and the point where I stop, okay, then I calculate what's the time. So in this case it will be 3 pi minus pi, so it's 2 pi, okay. So the fundamental period is 2 pi second, and the fundamental frequency is 1 over 2 pi hertz, okay, and the angular frequency will be 2 pi f, or 2 pi over t, so it will be 1 radian per second. Okay, so now that's easy. Now let's have a look at a different say type of question that can be asked with regards to a periodic signal. Okay, so in this case we are asked to again find the fundamental period, fundamental frequency, and the angular frequency, but this time instead of a graph we are given equation. Okay, so for question number 1 here we are given 10 cos 50 pi t. So when facing a question like this, I always teach my student, the first step is you make this equation equals to the general form of cosine function, which is a cos 2 pi ft. Okay, and then next you make the terms inside the bracket here equal, okay, so then you will get 2 pi f1 t equals to 50 pi t. Okay, so then we can calculate f1, this is just f, so we can calculate f, which is 50 pi t over 2 pi t. So this cancel out, and 2, this one will give us 25, so it's 25 hertz, right? So it means the fundamental period, which is 1 over f, it will be 1 over 25 second, and angular frequency, which is 2 pi f, or you can also use 2 pi over t, it will be 2 times 25, so it will be 50 pi radian per second. Okay, now let's have a look at the next one. Right, so this time we are given again a cosine function. Okay, now this one you can also make it equals to the general form of the cosine signal. So in this case we have tan cos. Okay, so the first part will be the one that contains the fundamental frequency 2 pi ft. Okay, plus this one is just the phase angle. Okay, so the one that is of our concern is the first part here. Okay, just make it equal, and then you can calculate for f. So again 2 pi ft equals to 30 pi t, right? So we can calculate f, which is 30 pi t divided by 2 pi t. So we will have this cancel and 15 hertz. Then we can calculate the fundamental period, which is 1 over fundamental frequency. So it will be 1 over 15 second. So and we can calculate the angular frequency, which is 2 pi f. Okay, or you can also use 2 pi over t. So 2 times 15, it will give you 30 pi radian per second. Right, now let's have a look at the next question. Okay, so this time you are given g of t, which is the equivalent to the sum of a cosine function here and a sine function over here. Okay, right, so when we have this kind of question, the first thing that we wanted to do is determine the the fundamental period of this cosine signal and the fundamental period of this sine signal. Then once we get that, we can determine the fundamental period of this resultant signal, okay, g of t, using a method called least common multiply. Okay, now if you don't know how to use this least common multiply method, you can refer to one of my video. I explain about least common multiply. Okay, now let's proceed with this one. Okay, so for this one, for g1 of t, which is equals to cos 50 pi t, okay, again we make it equals to the general function of cosine signal. So we put a cos 2 pi, and I'm going to call this f1 of t. So if we make the one in the bracket here equal, so we are going to have 2 pi f1 of t equals to 50 pi t. So f1 equals to 50 pi t over 2 pi t. So I get 25 hertz. So t1 will be 1 over 25 second. And for g2, which is equals to sine 15 pi t, again we are going to make it equals to a general function of a sine signal, 2 pi. I'm going to call this f2 of t. Okay, so we make again this one, the one in the bracket, equal. Okay, so we will have 2 pi f2 of t equals to 15 pi t. Okay, so we can calculate for f2, which is 15 pi t over 2 pi t. So they cancel out, but these two cannot cancel out, so we leave it as 15 over 2 hertz. Okay, so our t2 will be 2/15 second. Right now we have two numbers. Okay, so let's try to solve over here. Now we have two numbers. I'm just going to change the color. Let's say I use green. So I have 1/25 and I also have 2/15. Okay, so now the next step is to multiply these two numbers with a common number so that we can make this non-integer number to be integer. Okay, so I think the common number is 60. 25 divided by 60. So nope. Right, so we can do this the traditional way. Let's try. We have 25 multiplied by 1 is 25. By 2 will be 50. Will be 75. Okay, so actually it's 75 and 75. So if we cancel 25 25 multiplied by 3 is 75. 15 multiplied by 5 will be 75. Right, so 3 times 1 it will be 3, 5 times 2 it will be 10. Okay, now we have this 3 is already a prime number, so let's just leave it like that. But this 10 we have to reduce to a prime number, so this will be 2 times 5. And if we look here, we have 3 to the power of 1. Okay, because this number 3 appear only once, while for this we have 2 to the power of 1 and 5 also to the power of 1. Okay, 2 appears one time here, 5 appears one time here. So the least common multiply for these two numbers will be 2, 5 and 3 all to the power of 1. It will give us 2, 3, 5. It will give us 30. Okay, and then the fundamental period for g of t, which is this g of t, will be 30 divided by 75. Okay, because at the beginning here, okay, we multiply the number with 75 so that this non-integer number, okay, will become integer, which is the requirement for the least common multiply. So when we calculate for the fundamental period, okay, the number that we get from the least common multiply method, we have to divide back with 75. Okay, so this will give, if we use, okay, we can reduce further. I think 15 times 6, no, 15 times, this one will be 2/5. Okay, now let's have a look. Sorry, and this is second. Okay, now let's have a look at this signal. Okay, we are given a tree now. Okay, a cosine signal, a sine signal and a cosine signal, okay, with a phase angle. Okay, so just like before, we call this g1 of t, we call this g2 of t and g3 of t. Now let's calculate one by one. Okay, we have g1t, which is equals to cosine of 2 pi t. Make it equals to the general function of a cosine signal and make the terms in the bracket equal. So we have 2 pi f1t equals to 2 pi t. Therefore we can calculate f1, which is in this case 1 Hz. And so we have t also 1 second. Okay, by the way, for this question at the top, okay, I forgot to calculate. F equals to 1 over t, so 5 over 2 hertz, and then the radial frequency, which is 2 pi f, will be 2 pi 5 over 2, so it will be 5 pi radian per second. Okay, now let's continue with this one. For g2 of t, we have sine 3 pi t, then we make it equals to a sine 2 pi, let's call it f2, so that we can calculate for f2. So t2 will be 2 over 3 seconds. Right. Now for, let me just use a different color. Maybe, oops, say a purple color. So g3 of t will be cos 5 pi t minus 3 pi over 4. Okay, can we make this equals to general form of cosine signal? So the one at the back there is only the phase angle. So our constant is this part. So we have 2 pi f3t 5 pi t. So we can calculate for f3. Which is 5 over 2 hertz. And therefore t3 equals to 2 over 5 seconds. Okay, now we have 3 numbers. We have 1, we have 2 over 3, and we have 2 over 5. Okay, so next we have to multiply these 3 numbers with a common number to make these 2 non-integer numbers to be integer. So 3 and 5, I think it's easy, which is 15. Right? So 1 times 15, we will get here 15. These 3 and 15 will cancel out, so we have here 5. 5 multiplied by 2, we get 10. 5 and 15 cancel out, we get here 3. 2 times 3 will be 6. Now next is to reduce these numbers to their prime factors. For 15 it will be 3 times 5. For 10 it will be 2 times 5. And for 6 will be 2 times 3. Okay. Now we check the frequency for each number. Here we have 3 to the power of 1 because it appears only 1 time here. Similarly 5 to the power of 1. Okay, 2 also to the power of 1. 5 to the power of 1. For the third number we have 2 that appears only 1 time, and 3 that appears only 1 time. So the LCM for these 3 numbers will be, we have number 2, number 3, and number 5. Okay, and in all cases, number 1, the frequency is only 1 time. Okay, so the common mistake that my student do is, because they see here 2 to the power of 1 and 2 to the power of 1, so when they do the LCM here, they make it 2 to the power of 2, which is wrong. Okay, we're supposed to take the number with the highest power. Okay, but here in this case we have 2, okay, both with the power of 1. Okay, so we take it here 2 to the power of 1. Similarly here 3 to the power of 1 and 5 to the power of 1. So if we calculate, we will get 2, 3, 5, it will be 30. Okay, so now T is equals to 30, and remember to divide back by the number that we use, okay, to multiply the non-integer number. So in this case it's 15, right? So we will have 2 seconds. Okay, so F, so the fundamental frequency will be 1/2 Hertz, and the radial frequency will be 2 pi F, so it will be pi radian per second. Okay, so that's how we solve this type of question, right? Next one, we have the energy signal. Okay, so here we are given an exponential signal, okay, that somehow is multiplied by a step signal over here, right? So we are asked to calculate energy. Hope you still remember the for energy, okay, the formula is integration from minus infinity to infinity for the signals square dt, right? Now if we look at this signal, we can see that it is divided to two parts. Okay, the first part we have this step signal, okay, from 0 to 1, okay, with amplitude of 2, and the second part is this exponentially decaying signal, okay, which is from 0 to infinity, okay, and this is the amplitude of the signal, or the equation for the signal. So it means when we calculate the energy, we have to calculate them separately. Okay, so we have from -1 to 0, so our signal is the step signal with amplitude of 2 dt, plus the one from 0 until infinity, and 2e minus t over 2 square dt. Okay, so this 2 is just a constant, so we can take it outside. We'll leave with -10 dt, plus here also we have constant to the power of 2, it will be 4, 0 to infinity, and then if we multiply these two with the power of the exponent, we will have e minus t dt. Now we integrate them. For the first part, we will have t only, -1 to 0 plus 4. This one we will have -1 e minus t. Sorry, no dt. Okay, so you can make it 4, 0 minus -1, and then we take this minus sign outside, we will have -4, and then here is from infinity to 0, so e to the power of minus infinity minus e to the power of 0. So if we take our calculator, this 4 times 1, it will be 4 plus, okay, this e to the power of minus infinity will be 0, and this e to the power of 0 will be 1. Okay, so inside the bracket it will be -1. -1 multiply with -4, we will get +4. So the power, the energy for this signal is 8 joule. Okay, right. Now let's have a look at how to calculate the power of a periodic signal. Okay, for example, like shown in this graph, we have a sawtooth signal. Right. So the general equation for power is 1/t t over 2 minus t over 2, the signal to the power of 2 dt. Right. So if we apply that, okay, we can integrate the signal over one period, okay, because we have a periodic signal. So the power for the signal over one period will represent the power of the signal for the entire time, for the time approach infinity. Right. So if you look at the signal here, let's say we start from here, the point 0, 0.00. If we go up, we go down, and we go up here, and we stop here, okay, and then if you go up again, we're going to repeat the same cycle. So it means from here, t equals to 0 until t equals to 2, we have our period, which is equals to 2 seconds. Right. So what we do is we replace this 2 seconds into here and into the limit of the integration. So we will have 1 over 2. Okay, 2 over 2 will be 1, and here is minus 1, and the signal is the slope, okay, of this slope is t, okay, and this slope is also t. So we will have t square dt, okay, for the entire period, okay. So we will have 1 over 2, this is 1 over 2, 1 over 3 t cube, right, and 1, 2 minus 1. So this multiply, we will have 1 over 6, and this one will be 1, and then minus 1. Okay, if we substitute this one, okay, to t, we will get positive 1. If we substitute minus 1 to this t, okay, minus 1 to the power of an odd number, it will be minus. Okay, so we will have here 2 over 6, so we have 1 over 3. Okay, so the power for this signal is equals to 1 over 3. Right. Now in class, I also say that we have a relation between power and root mean square, or RMS, where P equals to RMS square. Okay, so let's say the question asks you to calculate the RMS for this signal. Okay, you can find it, okay, from the square root of P equals to RMS. So in this case, for this particular signal, it will be 1 over square root of 3, okay, the RMS of the signal. Okay, and right, in the next question, we are given 4 different signals. Okay, so let me just call this signal A, signal B, C, and D. Okay, so the question asks us to show that the following signals, okay, have 4J, energy of 4J. So this is for signal A, 1J for signal B, 4 over 3J for signal C, and 4 over 3J as well for signal D. Right, and we know that the equation for energy is equals to integration from minus infinity to infinity, okay, which is wherever the limit of that signal, equation of the signal square dt. Right, so let's have a look for the first signal, right, for A. So the energy will be, right, the limit first, the integration limit. So if you look this signal, okay, it looks like this. Okay, so I mean we wanted to integrate from 0 to 1. Okay, and this is a pulse square signal, okay, rectangular signal like this. So the amplitude is 2 dt. In this case, it will be 4 1 2 0, and then if we replace, sorry, there's a confusion there. It says 4 and then t, 1 0, right? So 4 1 minus 0, so it will be 4. Now let's change the color. 4c and 4b, right? Again, ex equals to, what's the limit for the integration? So the signal is from 0 until 1. Okay, so 0 to 1. What's the amplitude of the signal? Is 1. So it will be 1 squared will be 1. So let's put it as dt. So ex equals to integration from 0 to 1. Okay, so ex equals to 1. Okay, so in this case we prove this to be true and we prove this to be true as well. Now let's have a look at C. For signal C, ex equals to integration. So again, this signal, it goes up, goes down, and dies out at 1. Okay, so it's from 0 to 1 again. Now here we have a signal, okay, with a slope. So if you look at the signal here, the slope will be 2t. Okay, so we have 2t square dt. Okay, and if you don't know how to determine the slope by looking at the graph, you can calculate the slope, okay, using the usual formula, okay, for slope of a straight line. Okay, this one, you will get this one. Okay, now this 2 to the power of 2 will be 4, and we have t square. So this will be 4 t cubed over 3, 0 to 1. So it will be ex 4 over 3 joule. Now let's have a look at the last one, okay, which is D. So ex will be, so now the signal is shifted. Okay, if you see, this x4 is actually x of t, okay, x of t, but shifted to the left 1 unit. Okay, so now we have the limit from -1 to 0. The signal is the same, okay, because the slope is the same, dt. So ex equals to again -1 to 0 t square dt. Okay, and if we solve, we will get 4 over 3 t cubed, 0 minus 1. And if you solve, you will get 4 over 3 joule. Right. Okay, actually this question, the question wanted us to see is that, for example, for signal 1 and 2, or signal A and B, okay, signal A, the amplitude is 2, okay, signal B, the amplitude is 1, but they are the same rectangular pulse signal, except that for signal A, x1 of t, right, the amplitude is 2 times of signal B. And we can see that when the amplitude is increased, okay, from 1 increase to 2, okay, the amplitude is double, the energy becomes quadruple. Okay, from 1 joule it becomes 4 joule. Now for the signal C and D, we can see that when the signal, okay, x of 3 is shifted to the left 1 unit, okay, the energy is still the same. So it means shifting, okay, the time, okay, of the signal will not shift the energy, or will not affect the energy of the signal. However, let's say x of t, and let's say we have x5 of t, which is x of 3 and let's say 2t. Okay, the signal is scale instead of shifted. So in this case, from 0, okay, the 0 will remain at 0, but the time 1 here, okay, because you scale by 2, so 1 will become half, and the amplitude stay the same at 2. Right, now you have a signal like this. So if you calculate, then the energy will be different, because now the signal becomes smaller. Or let's say if you have x6 which is also xt, but the time is scale, let's say by half, and we learn that when the time is scaled by half, so it means the signal will be enlarged, okay, with respect to the x-axis. So here 1, so instead of 1 it will become 2. The amplitude will remain at 2. Okay. So now here you will see, if you have a signal like this where the time is scaled, you will see that the energy will change. Okay, you can try that on your own. Let's have a look at the next question. So in this question, we are given 4 graphs as shown here, and we are asked to determine whether the signal is even or odd. Right, now let's have a look at the first graph. So this is the y-axis, okay, and we can see that this signal, okay, or rather this part of the signal, okay, where the time is positive, is the mirror image of this part where time is negative with respect to the y-axis. Okay, so this signal is even. Okay, and if you recall that for even signal, let me just write up here. Okay, a signal is even if and only if y of t equals to y of minus t. Means the same value of signal, okay, or the same amplitude, let's say the same amplitude, okay, occur at a positive time and at the negative time. Now let's have a look. Let's say this is 1 over 2 and same point minus 1 over 2. Okay, so they the same time, except that this one is positive and this one is negative. So if we look, if we project up, let's say over there the amplitude, and we project up as well, let's say the amplitude over there, so they have the same amplitude, okay, when time is positive and when time is negative, which means we satisfy the equation that y of t is equals to y of minus t, or rather f actually, because it's a function. Let's change it to f. Okay, ft is my f minus t. Okay, let's have a look at this signal. Let's call it number 2. Now if we see this signal, this is the y axis. So this part of the signal, which is the positive t, and this part of the signal, which is with the negative t, they are not the mirror image of each other, so we know that this is not an even signal. Okay, however, is it odd? Okay, now let's have a look at the definition for odd signal. So a signal is odd if and only if f of minus t equals to minus f of t. Okay, so means the amplitude of the signal at negative at time negative, okay, you will have the same value at time positive but the inverse of each other. Okay, so let's say this point here, which is between 0 and pi, so let's say this is minus pi over 2 and this is pi over 2. Okay, so here the amplitude, here let's say 2, wherever for this one the amplitude is minus 2. So you can see this signal, the time is positive, the amplitude is negative. For this signal, the time is negative, okay, which is here time negative, and the amplitude is positive. Okay, so amplitude is positive. Right, so we can say that this signal is an odd signal. Right. Okay, now let's have a look at question number 3. Okay, so this is the y-axis. Again, if we see this part where t is positive and this part where t is negative, if we see they are not the mirror image of each other, so this is not an even signal. But is it an odd signal? Okay, now let's have a look. Say this point, okay, the amplitude is positive 1 2 3, so let's say 4, and this point, let's say this is pi, I don't know, pi over 4 maybe. Okay, and this point is similar to this point, okay, in terms of time, say minus pi over 4. Okay, if we take it down, then they say they have the the inverse amplitude. So this one is minus 4. So we can see that the f of minus t is equals to f of minus f of t. Okay, because their amplitude is the inverse of each other. When this one amplitude is positive, this one amplitude is negative. Okay, so this is an odd signal. Right, and also another a method to see whether that signal is odd or even. Okay, one of the textbook that I read says that an odd signal, it must pass through the origin. Okay, for example here this is the origin, okay, 0 0. Also here this is the origin. Okay, so this signal is on an odd signal. Okay, but when it passes through the origin, it is not necessarily an odd, it can also be an even. But if you look at signal number 1, okay, this signal doesn't pass through the origin, therefore this signal cannot be odd. Okay, so it can either be even or neither odd neither even. Okay, so let's have a look at the fourth signal. You can see that it is passed through the origin, but is it an odd signal? So we look at the y y scale, okay, and the y-axis. So we can see that this part, okay, where t is positive is equal to this part where t is negative. Okay, so they are the mirror image of each other. So this is an even signal. Right. Or you can also check if you want. Let's say if this is 2, this is minus 2. If you take it up, here say this is the amplitude, say maybe 1. Okay, so at t positive, you have the same amplitude. So we satisfy this equation. Okay, at time positive and at time negative, they say they have the same amplitude. Okay, now let's have a look at another form of question related to even and odd signals. Okay, can be asked in the exam, for example. Now we are given an equation instead of a graph, and we are asked to determine whether the signal is even, odd, or neither. Okay, so here we have a sine function. So one method to solve this is if you draw the sine functions graph. So you will know that from the graph you will know that it is even or odd, or maybe neither. But let's say you don't remember how the sine graph looks like. Okay, so here I'm going to teach you a method where you calculate the value of sine at different time. Okay, so to check for evenness, okay, we use f of t equals to f of minus t, and to check for oddness, we use f minus t equals to minus f of t. And if it doesn't satisfy both equation, then we say the signal is neither even nor odd. Okay, so f of t in this case is sine of t. Okay, and we are going also to have f of minus t, which will be sine of minus t. We are also going to have minus f of t, which is minus sine of t. You know what we are going to do? We are going to calculate the value of sine t, sine minus t, and minus sine t at different value of t. Okay, you don't have to use too many, just so that you can see the pattern. So let's say maybe we try 2 and 4. Okay, that's actually enough for us to look at the pattern. So you try sine t. Take your calculator and press sine 2. So it will give, let me just change the color so we can see, 0.0349. Now if I press sine minus 2, I get minus 0.0349. And if I do minus sine 2, I get minus 0.0349. Actually from this one you can see the pattern already, but for the sake of argument, let's say we calculate sine of 4 as well. So 0.0698, and if we do sine of minus 4, we get minus 0.0698, and minus of sine 4 we get again minus 0.0698. So from here you can actually see that, I'm just going to delete this. You can see that these parts are equal, which means f of minus t equals to minus f of t. So we satisfy the equation for oddness, so it means we have an odd signal. Okay, now let's have a look at this one, cos t. So again, this is a simple signal. So like I said, if you remember how the graph looks like, so maybe in the exam you can draw the graph and say that, okay, from the graph the signal is even or odd or neither. But let's say you don't remember how the graph looks like. Okay, so let's just do the use the calculation. So we have f of t equals to, oh sorry, this is a cosine, cos t and we have f minus t, which will be cos minus t, and minus f of t will be minus cos t. So again we try at different value, and let's just use the same value, t, 2 and 4. So we take our calculator and we do cos 2. It will be 1. And cos of minus 2, 1 as well. And minus cos 2, it will be minus 1. Okay, I think you can see the pattern now, but let's just proceed with cos 4. Well, it's a 1 as well. Cosine of minus 4, it's a 1, minus cosine of 4, minus 1. So we can see that these parts are equal, which means f of t equals to f of minus t. So we satisfy the evenness equation. So this is an even signal, right? Oh, now we have a signal, okay, which is the result of multiplying a sine and cosine signal. Let's try use the same method. So we have f of t equals to sine t cosine t. For the second one, we need f minus t, which is sine of minus t multiply with cosine of minus t. The third one, we need minus f of t. So it will be minus sine t cosine t. Right, so let's say we use t let's say 10 and 20 maybe. Let's try. So we have sine 10 multiply with cosine 10. We have 0.17, 0.171. Now sine minus 10 multiply with cosine minus 10, we get minus 0.171. So minus of sine 10 multiplied by cosine 10 will give us minus 0.171. Let's just calculate the next one. Sine 20 multiplied with cosine 20, 0.321. So sine of minus 20 multiplied by cosine of minus 20, negative 321, and minus, again we get minus 0.321. So we can see this time we have this part equal, which is the f minus t equals to minus f of t. So we have an odd signal. Let's have a look at the next one. Okay, t sine t. So let's do the same. Ft is t sine t, and oops, we don't need that much. Just going to delete. Now f of t will be minus t sine minus t. And minus f of t will be minus t sine t. So let's try t with 10. Let's try using only one number. So we will have 10 multiply sine 10, 1.736, and then we have minus 10 multiply with sine of minus 10. 1.736. And we have minus 10 multiply with sine 10. Here it's 1.736. Okay, so we can see that this part are equal, which is f of t equals to f of minus t. So we have an even signal. Right, now for this one, I'm just going to, because there's no sine or cosine, so we can use much simpler. So we have f of t and we need f of minus t. Okay, so it will be minus t square. Now a negative value, if we to the power of even number, it will give us a positive value. Minus f of t is minus of t square, so it will be minus t square. So from here we can see that f of t is equals to f of minus t. So in this case we have an even signal. Let's have a look at the next one. Oh, now we have addition of sine and cosine. So what happens if we add sine and cosine? So here we use the previous method. F of t is sine t plus cosine, and f of minus t will be minus of the t plus minus t, and f minus f of t will be minus sine t plus cosine t. Okay, now let's say we use t equals to 10. So take our calculator and let's calculate sine 10 plus cosine 10. We get 1.158. If we do sine of minus 10 plus cosine of minus 10, we get 0.811. And if we do minus of sine 10 plus cosine 10, we get minus 1.158. Now we see that this part, f of t is not equals to f of minus t. And similarly, this part, f of minus t is not equals to minus f of t. So we does not satisfy the evenness. We also doesn't satisfy the oddness requirement. So this is neither even nor odd signal. Now let's have a look at the next one. So we have here f of t given by this equation. So we don't have a sine or a cosine function, so we can do like this. We need f of minus t. So let's change all t to be minus t. So here we have t, so we will make it minus t, plus 3 minus t to the power of 2, we will get t. Okay, minus t for this one, minus t to the power of 3, we will get minus t. So minus 5t to the power of 3. and minus t to the power of 4 will get positive. And for minus f of t, it means minus 1 plus t plus 3t squared plus 5t cubed plus 9t to the power of 4. Okay, so minus with so everything minus 1, we will get minus 1 minus t minus 3t squared plus this is minus minus 5t cubed minus 9t to the power of 4. Okay, now if we look, this is f of t, so f of t, this is f of minus t, they're not the same. And because at f of t everything is positive, but at f minus t we have this minus, we have this minus. Okay, so we can say that f of t is not equals to f of minus t. And if we compare f of minus t with minus f of t, they are also not the same, right? Because for f of t only these two part negative, but for minus f of t everything is negative, right? So they are also not the same. So this is again neither even nor odd signal. Okay, so I think that's the end of the question. Right, so thank you for watching, and I will see you again in the next video, where I will discuss more sample question related to signal and system analysis. Thank you.